Welcome to our conversation on artificial intelligence, machine learning, and deep learning, and really what impacts it's going to have for business going forward. There's been a lot of discussion in the press in recent years on the impact of artificial intelligence and how this is going to revolutionize the way governments and industries and businesses will be running. And I believe it truly is going to be that case. Matter of fact, you can see a lot of this impact from just the number of mentions of AI on earnings calls from public companies. And when you take a look at what's happening in the merger and acquisition space, you can see the value of those mergers and acquisitions that are happening for artificial intelligence, not to mention the number of deals that are happening, as you can see that the Economist reported here in PitchBook. I truly believe there's going to be a big impact for all business leaders in the future. You can tell because global spending is growing at 50% compounded annually and is expected to reach $57.6 billion by 2021. So you're talking just about every industry is going to have a benefit from this if they do it correctly. Healthcare, marketing, fintech, obviously retailing is going to do a lot of work in this area. And it's interesting because the companies that are really embracing artificial intelligence are going to see a take of over $1.2 trillion a year from those companies that do not take in this type of intelligence into their business planning. And that's according to Data Robot by the year 2020. And you can see this very clearly with Amazon. Amazon is using the data they have inside their enterprise to be able to leverage that knowledge into other areas, from retailing to entertainment, to delivery and logistics. So this is just one prime example to be able to see what I'm talking about here. Matter of fact, 83% of the early adopters of artificial intelligence are already seeing value gains in what they're doing by having these initiatives come into their enterprise. And there's been a lot of talk about jobs, and we'll talk about that in just a bit, but according to Data Robot, they see a net increase in this AI adoption of over 5 million new jobs in the United States alone. Now, of course, that's going to be an adjustment of jobs as some of the more menial labor positions get taken over by machines, but it could be a net benefit because of the power that's going to happen within our economy because of this. Now, many of you have heard about the term that data is the new oil. And this was at a time when, during the Industrial Revolution, where oil was really the base of that. Oil was what enabled the Industrial Revolution to have. And that could be from manufacturing, transportation, automotive, or power generation. And of course, the big company there was Standard Oil Company. But I believe data is what is going to enable the digital revolution, much as oil is the new data, but you could take those exact same industries, manufacturing, transportation, automotive, and power generation, and see how data is in altering these industries in this new digital revolution. And we have many companies here, from Tencent to Alibaba to Amazon to Google, that are really taking advantages of this new data revolution that's happening. So as business leaders, what you want to do is think beyond just the data resource itself and see what new paradigms are going to be created from this, because I believe data is going to be the base upon which these new paradigms are created in your industry. So let's talk a little about the three here and really their interaction and play with one another, starting with artificial intelligence and then moving into machine learning and deep learning. Now, there is a natural evolution for technologies to move from one capability to the next. So we started with cloud computing, and when we had cloud computing, it really was what enabled us to have these large data sets accessible, so we could actually get to them. And then once we could get to them, we could develop them. And that's where big data came in, because it really enabled us to develop these large data sets. And once we had the large data sets, then we could really analyze them and figure things out. And this is what machine learning is doing today. It's utilizing very large data sets and analyzing better ways to do a particular task. And the machines are learning over time with these models to be able to come up with better information and a better analysis. And that's now leading us into artificial intelligence, which once we have the data analyzed, we can then understand it. And if we have an understanding and the machine knows what's there, then we can have it do things that would make sense based on the data that it sees, because it understands what it would need to do. It's like, there's an issue, here's a problem, here's something that needs to be fixed or resolved or improved, therefore take the appropriate steps to do so. And these are naturally building upon themselves. But for this particular section with AI and machine learning and deep learning, they're actually subsets of them, and oftentimes you'll hear them intermixed when really they shouldn't be. Artificial intelligence is the overall encompassing component of this, which is really, it's a technique upon which machines mimic human behavior. They don't really think, but we're thinking of it in that way to describe it here, of saying they have artificial intelligence and they think like a human might. And of course, a subset within that is the machine learning. And this is really the techniques and statistical methods we use to enable machines to improve over time with experience. We're building models that they learn from, and they try to make the model better and better and better. And it's an iterative process. And within those model buildings, we have something called deep learning, which is a subset of machine learning. And it's basically this value of the computational network in a multi-layered neural network within the machine learning model itself. Much like the human brain utilizes information between its cells to actually figure things out from pieces of knowledge that it has. Now, a lot of times when you'll hear these things, you'll hear that AI really doesn't require any coding. You just bring your data and it works. Or that the machine learns from the data naturally and there's no human involvement that's required to do so, which obviously isn't the case. And then the other thing is the machine's just going to figure it out for you. There's some of this truth to some of these, but it doesn't really work that way. And that's why I wanted to spend some time with you on this video to talk a little bit better, more about that and a little bit deeper. Please watch this little short video that'll explain how these three items work together with artificial intelligence, machine learning, and deep learning.
Artificial intelligence, machine learning, deep learning. For anyone who's not a data scientist, the terms associated with computing's next big wave can be pretty confusing. But at the most basic level, the relationship between these three key concepts is fairly simple. Artificial intelligence refers to the broad category of computing in which a system is capable of learning directly from data, a capability made possible by the advent of data analytics and applied either through a set of rules that are evolved over time through human intervention with the system, or increasingly through the process of machine learning, in which the system expands its ability to process and use information without the need for additional human intervention. While the broader concept of artificial intelligence has been around since the 1950s, it was the introduction of machine learning in the 80s that brought the first real wave of significant advancements to the field. Then, as computational performance reached a tipping point in the last decade, a new wave of even more dramatic breakthroughs began to gather momentum. Deep learning is a branch or subset of machine learning that leverages those computational advantages and a set of new techniques, such as neural networks, to make sense of and learn from even larger amounts of data. The result has been an impressive acceleration in the progress of elusive artificial intelligence capabilities. Capabilities like image, speech, and natural language recognition that promise to have a significant positive impact on our everyday lives. The emergence of deep learning also serves as a reminder that the technology and techniques for achieving the full potential of artificial intelligence are not static, but will continue to evolve just like us.
So let me give you a small example now that you've watched that video that we're all probably very familiar with, and that is frequently asked questions. This is a very simple example. We probably have all developed frequently asked questions for our corporate websites. We do this as a customer self-support. We want to really try to help customers help themselves. And we've thought through what they might ask. We've looked at the historical nature of what they've asked in the past. Maybe we've gone to our customer support team and asked them. And we really want to cut costs, but more importantly, we want to enable customers to help themselves so they lower their customer frustration and allow them to be able to ask their own questions. So the good thing about this is AI can kind of address those customer needs and basically provide the information they need when they need it and as these customers ask it, and actually increase engagement in the process. And the good thing about this engagement level of the machine coordinating and communicating with their customers, they learn a lot more about them, and they're able to capture and grab that data and get smarter and better over time. The good thing about this is has it really been put into place? So let me give you one example that's actually at the Cosmopolitan Hotel in Las Vegas. They now have a new bot that will be almost your own personal concierge. Her name is Rose. You can text Rose. You don't even have to be a guest that stays there. This is her number on the screen. And basically she provides information back to the customer that they might ask. Where is the best restaurant in town? Can you get me a reservation there? What's their next opening? What bar would be the best one to go to on a Saturday night at midnight? This bot actually has a conversation with you. Now, we don't know exactly what all is going to be asked of her. We can't possibly code everything that she might be asked from their customers, but they have created models, which is the artificial intelligence piece, to respond appropriately. Now, interestingly, she does tend to recommend things that are at the hotel itself on site, and they've even seen a 39% increase in spending since they've enabled Rose. But really, what's really good about this is 90% of their guests remember her. They would recommend her. They actually enjoyed the process. And as she gets more improved, she'll be able to speak in any customer language. So you'll speak in the native language of the customer itself. And the hotel is mining this information that customers are asking Rose to understand what it is they need and to get better over time for meeting customer demand. That's what we want to learn about there. So machine learning is really this next step in the business evolution process. And really we want to understand what machine learning is. And it's really this idea that a computer program can be adapted with new data independently without a human having to get involved and do a lot of specific coding. It's really the science of getting computers to act without explicitly being told step by step, program by program, what the component piece that you need to resolve this issue, this question, or whatever component data that you're being prescribed. Because if we don't know what our customer is going to ask to Rose, this automated bot concierge at the Cosmopolitan Hotel, we can't possibly program it. So since we don't know what is going to be asked, we won't know the programming piece. So that's why we have to figure out these models within machine learning. And we build a model within the machine that allows us to improve over time. And the way you do this model building is we would capture the data with answers. We would clean it, prepare it, and manipulate it. And we would train a model behind it. So we would ask the same questions for the answers we know, see if the model got it correct. If it did, we move forward. If it didn't, we go back and refine the model. And this is where we do this testing of the data. And if it doesn't come out with the test we like, we improve upon it. And we're building a model for how the data would be responded to, not the actual coding of lines itself. So why don't we watch this little video that'll help you understand how this model can actually be affected by the humans that are creating the model, even though they may not be aware of it. And there's some human biases that may come in.
Let's play a game. Close your eyes and picture a shoe. Okay, did anyone picture this? This? How about this? We may not even know why, but each of us is biased toward one shoe over the others. Now imagine that you're trying to teach a computer to recognize a shoe. You may end up exposing it to your own bias. That's how bias happens in machine learning. But first, what is machine learning? Well, it's used in a lot of technology we use today. Machine learning helps us get from place to place, gives us suggestions, translates stuff, even understands what you say to it. How does it work? With traditional programming, people hand code the solution to a problem, step by step. With machine learning, computers learn the solution by finding patterns in data. So it's easy to think there's no human bias in that. But just because something is based on data doesn't automatically make it neutral. Even with good intentions, it's impossible to separate ourselves from our own human biases. So our human biases become part of the technology we create in many different ways. There's interaction bias, like this recent game, where people were asked to draw shoes for the computer. Most people drew ones like this. So as more people interacted with the game, the computer didn't even recognize these. Latent bias. For example, if you were training a computer on what a physicist looks like, and you're using pictures of past physicists, your algorithm will end up with a latent bias, skewing towards men. And selection bias. Say you're training a model to recognize faces. Whether you grab images from the internet or your own photo library, are you making sure to select photos that represent everyone? Since some of our most advanced products use machine learning, we've been working to prevent that technology from perpetuating negative human bias. From tackling offensive or clearly misleading information from appearing at the top of your search results page, to adding a feedback tool on the search bar so people can flag hateful or inappropriate autocomplete suggestions. It's a complex issue and there's no magic bullet, but it starts with all of us being aware of it so we can all be part of the conversation. Because technology should work for everyone.
So as you can see, as we build these models out, you have to really take into consideration that humans are being involved in this process. So let me give you one example from Amazon that I thought was really interesting. If we look at the charts here on the left about the makeup of the high-tech industry from major firms, blue being male, red being female, you can see it's a predominantly male-dominated industry. And if we go down to the lower section where you see technical roles, it's even more dominated by men. So Amazon wanted to use artificial intelligence to avoid any gender biases that might come in to their hiring process. Because they thought, well, if we can have a model that does this correctly and a machine describes it, it won't have any prejudice against men or women, and it will actually get more appropriate to where the world's population is more 50-50. So they had a machine pick out the best candidates regardless of gender, but they had to realize that they were training this model based on successful candidates in the past. They used resumes over the last 10 years, and unfortunately that data was very skewed towards men. So the training data set that they created was actually becoming more biased towards men because it had the training itself of men's resumes and men's information in the system. So once Amazon realized this, they stopped using it. But it's a good example of how these biases could come in even if we don't mean for it to be. Because when we do these machine learnings and we try to train these models out, we give input data to the machine, but we're also giving it the answers to those questions that we're providing to it. So it's looking for patterns, it's looking for relationships, it's looking for dependencies and hidden structures within that data. And then we look for a model that would produce that output. So since we know the question and we know the correct answer to the question, could we feed it an answer, a question we don't know, and it come up based on the model with the correct answer? That's the goal anyway. And so there's some multiple ways upon which we can do machine learning: supervised, unsupervised, and reinforcement learning. So supervised learning is very task-driven. We predict the next value. This is where we have the humans involved. In the unsupervised version, it's very data-driven. We're looking for clusters. We're looking for similarities within the data itself. And it's reinforcement learning. We're trying to teach the machine to learn from its mistakes. So if the machine comes up with a bad answer, bad machine, go back. We try to put in an algorithm that says try to get the best score, get the best answers, and the machine includes its learning over time, which takes a while through reinforcement. So let me talk to you a little bit about those two most common, supervised and unsupervised. So in supervised learning, we are feeding data to create this model that has known labels. We know exactly what we're looking for, has very specific output. So a good example here would be fraud detection. We know what fraud looks like in the financial services industry. We can give it a set of data of known fraud issues and say, if you see this type of pattern in the data, it's fraud. We can verify it, flag anything that looks like this. So in unsupervised learning, we're just feeding it a bunch of data, but we don't know what we're looking for. We don't know what the data labels are. What we're seeking in unsupervised learning is patterns. So we're asking the machine to go through all these big sets of data and find things that are similar, find things that are alike to find a pattern. We don't know what those patterns are, but just go find the ones that you can see. And the machine does that very well. So a good example here would be customer segmentation or clustering of our customers, because we know we have lots of customers, so we can feed in all the customer database and say, go look for patterns within those customers and group ones together that are similar. I don't know what similarity means, but just go find those similarities that you discover after looking through all the data. So this really helps us out. So in supervised learning, we're predicting values for known targets. So remember, we're feeding in information that we know what the answer is going to be. And two very common areas that we see here is regression, for typical regression analysis, or classification, where we're looking for classes like as a Boolean or categories or discrete values that we're seeking out. So if we have a regression analysis, we're very familiar with that in our MBA programs of how far away they are from the line and what the R-squared value looks like. Or if it's classification, such as this is a bull market or this is a bear market, because we can see values in the stock market overall going up or down in general. So we can classify based on the data we're seeing what type of market this is. Now, unsupervised learning, we're looking for basically structures within the data, but we don't know what those structures are. Unknown targets, if you will. So cluster analysis or density estimation or dimension reduction is a good example here, where we're trying to group and cluster and find where the densities of these informations are, or reduce pieces where we don't see a lot of density. So we're looking for those clusters within the data itself. Now these all come together in different types of machine learning, as well as included with reinforcement learning. So you think of it almost like gaming theory, that you teach the machine to get the best score, the highest score you can, to learn from the mistakes. But all three of these, whether it's clustering or dimensionality reduction through unsupervised learning, whether it's classification or regression through supervised learning, or just that reinforcement learning, all of these can be considered machine learning, and each have different things that they might want to do to provide. This slide here provides you all those different areas, from visualization to forecasting to predictions to customer segmentation, of where those could be used. Now let me give you a little example that might help explain this as well. In this example with the orange box, if you will, a yellowish orange box on supervised learning, we have 5 animals here. We're going to feed the animals into the system, and we tell it to the first animal is a duck, and the second animal is a duck. The third animal is not a duck. You don't need to know what it is, you just know it's not a duck. Same with the hedgehog. The next one down is not a duck. So we create a model there, and then when we feed in a 5th animal at the bottom here, we say, based on what we've told you, this is either a duck or it's not a duck, and we've told you what a duck looks like, is this animal a duck or not a duck? And in this model, the computer will look at it and say, yep, it has feathers, it has a bill, it has webbed feet. I believe it's a duck based on the prediction model that I've created. And so that's where you would see it as supervised. We're actually helping the computer by supervising it, if you will, letting it know what the data could be. Now, in an unsupervised learning algorithm, we're just going to say these are 5 animals. We don't know what they are, you don't know what they are, but go cluster them. So animal 1, 2, and 5 look similar. They all have feathers, they all have webbed feet, they all have a bill. I don't know what those animals are, but I'm going to cluster those 3. The third one down, the bunny rabbit, or the 4th one down, the hedgehog, those are different. They don't look like other things I see in this data set, so I'm just going to put them off to the side. So in this case, we'd be looking for those patterns to be able to say, the next animal that I give you, what do you think it is? And it will put it with the appropriate cluster. Now, which one of these do you think might be more expensive to do? In this case, it would be supervised learning, because you're having to have a human involved. You're having to have a very good, well-defined data set that takes a while to develop. You have to put some time and effort and energy to it. So those take a little bit longer to develop. And so supervised is going to be a little more expensive. But which do you think would have more errors associated with it? That would be the unsupervised learning. Initially, at least, you'd have more errors, because it's just going through and crunching, looking at all this data, saying, what does this look like? What does that look like? And it'll take longer and longer for it to try to figure out these patterns, but eventually it will. These are things you need to take into consideration as a business leader, because in supervised learning, you're going to get these training data sets, if you will, to make your model. Here we see sample 0, 1, 2, all the way through M, if you will. And you have a clean, highly defined data set with a known result, what results you're expecting from it. You feed it into the model, and then you can feed in some other item for the same sample data set, for a data set, if you will. Compare it to what you expect it to be, see if this prediction is correct, and if it's not, we have an error rate, and then we go back and we refine the model, and you want to get the error rate as low as possible. In the example with the unsupervised learning, here's a good example of a training data set of multiple shapes and colors. You would just feed it into a model and say, hey, go find things that look alike. So you can see it finds the green circles and ovals, it finds the blue squares, it finds the kind of orange and yellow triangles. But even at the bottom, they look similar, somewhat similar color, somewhat similar shape, but not 100%. It just starts finding patterns within the data. And that allows us to be able to feed in new things to say, which one do you think this would be based on those patterns that you've already identified. It helps it learn. So as you can see here, things will go through machine learning by utilizing something with a human involved. So let's take an example with faces, if you will. Let's say we wanted the machine to identify a human's face. So we can use a person to tell a machine what a face looks like. It has two eyes, it has a nose, it has a mouth, you might see ears on the side with hair on the top. This is a human getting involved, showing the machine what these features of a image of a face should be, and then from there we can turn it over to the machine and say, okay, now go use classification of all these features that you've extracted from the photo that we've told you about, and determine, is this a face or is this not a face? And you help me, figure that out. On a deep learning model, you could do the same thing, but you're asking the machine to do even more. You go figure out what the features are, you extract those features out, and then you classify them based on those features. And then you tell me, is this a face or not a face? And obviously there's many more layers that the machine would have to go through to try to figure that out. So if we look at the way these layers go, it just gets deeper and deeper and deeper because it has to think through, first of all, is this a feature in the photo? If it is a feature, is it a feature of a face? And if it is a face, does it match a classification of what I think a face is? So you can see there's much deeper level thinking, just as we do with humans in our brain. And that's where the concept of machine learning and deeper learning come about. So if a machine is going to use deep learning to identify a face, it'll go through multiple layers of these thought processes, if you will, of how it would look at that. So the first layer it's going to look at is edges within the photo. So it's going to look for pixels within the photo that have dark edges next to light or light next to dark. And it will say, oh, this must be an edge of a shape, if you will. And in the next layer, it says, now that I've identified those edges, do those edges form some type of feature, some type of shape that I recognize, such as an eye or a nose or a mouth? And if I've identified those features, such as an eye, nose, or mouth, are they in the appropriate location and dimension that I'm expecting of two eyes over one nose over one mouth? If those fall within parameters that I'm used to thinking about for a face, then can I then detect and say, yeah, this is a human face from it? And you see these nested hierarchies of how it would go further and deeper down into the data itself just by looking at pixels of a photo. So it will take this first input layer of these images of faces, and you would feed lots of them so it could learn from it. It would look for these patterns of contrast that will then go through more and more deeper layers to say, okay, now that I've identified the contrast, are they facial features? If they are facial features, do they actually match into a face? And I can go further and further down, like, does this face match a known face that I'm familiar with, such as a particular person, and therefore I could clearly identify this photo of this thing that I've identified of a face is indeed this person. So this is how this works. We can also do the same thing with speech recognition. So another good example, you're probably familiar with audio, analog audio waves and how they look. We can convert those to a digital signal for digital conversion. And once we have that in a digital conversion, we can look for patterns. We can go up to the cloud in large data sets and look for pattern recognition to know what particular words that are spoken look like in a digital pattern. And if that's the case, we know what the word is, and therefore you can communicate with a computer, such as a smart speaker, and being able to leverage the power of the cloud that takes in that knowledge, looks for those same patterns through artificial intelligence, and based on what it's described, can effectively respond in an appropriate way to a question that you might ask it. So this is ways that machines figure these things out. So if we look at photographs and how these pieces come together, it basically is what's enabling a computer to see. And if you think about it for your own mind, one of the best ways you get information into your mind is your visual sight and what you're seeing. So there are things that a computer does, but it does it by video or for photo images or scanning of a room, if you will. So in this case, we see the classification photo beginning with a cat, and it's classified that photo as what it thinks is a cat, but it can also do localization. And you see a red bounding box around the animal itself that says, within this bounding box, I see an item, and I can localize it there and then classify that item as a cat. I can do object detection and see multiple items, whether they're animate or inanimate. You see a inanimate duck, but live animals of cats and dogs. And it can even go further within the bounding box itself and try to find where that object is to do instant segmentation to actually more clearly identify the background as well, to know that these animals are sitting on grass or in an outdoor setting with trees behind them. And so this is where we start seeing these components come together for problem solving. So deep learning tends to solve the problem end to end, whereas machine learning will break it down into different parts to be solved. So here's an example of multiple object detection within a photograph where the two are working together. So deep learning is actually looking at the entire photo and saying, okay, I see things in these pictures, and I'm going to put bounding boxes around them. And then within the bounding box, machine learning can step in and say, okay, based on the shape that I'm seeing in this first yellow box, it has four legs, it has hair, it has floppy ears, has a long nose. I think this is a dog. Or the second one with the bicycle says, I see the tires, I see the shape of what I think is a bicycle based on all the pictures that I've seen in the past, therefore I'm going to say it's a bicycle. And so these two pieces are coming together to be able to allow the computer to identify what it sees in its sight with this photo. And so you can see what it does. It'll take pixel by pixel of this picture, if you will, and it puts it on a grid, and it puts bounding boxes around a lot of things that it might see. But it has little confidence in those things. It just sees those are areas. So what it'll use is a cross probability map to say, yeah, this item that's over here that has similar color, has similar shape, it's connected with one another. It'll use that to actually improve upon its bounding box determination, and then actually do final object detection, as you see here, and then turn it over to the machine learning side to say, okay, I found something in this photo that's in this bounding box. You go tell me what it is from all the data that you have, and it'll have a whole set of bicycles and cars and dogs that it's looked at in the past to be able to clearly identify it. And we can use these things to be able to do this for live photographs, for moving video and pictures, for actual real-world things. If we're feeding a live video image into a computer, and the computer can very quickly determine what these items are as it looks through it. So if you're in an autonomous vehicle, and the computer's LiDAR is bringing information in from the outside world, and the cameras are recognizing things within its field of vision, you want to know that that big moving object over to your right is a car. Matter of fact, there's two cars over there. It can very quickly identify these things and start looking through. Now, obviously, as you start putting this into a more congested environment within a city, the amount of power that's needed to be generated behind these and all the data that goes behind this starts putting these bounding boxes on multiple things, and they start overlapping. And the computer's got to process information very quickly. This is a scene here in New York where you can see the number of things that a computer's visual imagery, if you will, has to quickly understand frame by frame, because all the video is a series of photographs, if you will, frame by frame. And putting bounding boxes on things that it thinks it sees, and then determining what is within that box. And you can see even the percentage of its level of confidence that this is a person, or this is a traffic light, or this is a car, or a pedestrian, or whatever that might be. And these images are coming in very quickly to the car. Then, if it knows what to do, then it can try to figure out, okay, this is what I need to do to be able to identify this. So this is a retail scene from an automated shopping site. And I want to take a few minutes to kind of explain to you what you're seeing here. In this type of model, the computer imagery is determining what these two customers are picking up. And you can see that it's not using sensors on the shelf, it's just using the visual representation of the things it's identified. So here's a prime example of where business leaders are taking these new technologies into new areas. Retailing will change because of what's happening here in the component piece of utilizing artificial intelligence to determine what someone picks up, or if they share it with a friend, or if they put it back on the shelf. Because if you know what someone takes from the store, then you can obviously charge them that amount and not have to have a cashier. So you can see these individuals sharing items from the store, putting them back in the wrong place, sharing them across one another, and they're even going to do things like picking up things in the wrong position. Now this lets you know that the computer, the vision of the camera is actually figuring these things out. Here's an example where we have a hidden item. Inside the cooler is a roll of toilet paper, another item within the store. And it recognizes that and it pulls it in together to say, I know this is what the situation is. Now, as these consumers pick up their items, they can go to final inventory and checkout, and the computer knows what all has been picked up and by whom. And you can see the different color changes there, and then be able to charge it correctly for the right spot. Let me go ahead and finish this out. The other thing that's really interesting here is the capability that we have for cars. So in this model, you start thinking about how the landscape of our cities around the world are going to change. This is a normal model with traffic lights and with cars that normally stop. This is what will be happening with autonomous cars. If the cars have intelligence and they can talk to one another and can talk to their surroundings by themselves, will we have traffic congestion like we've had in the past? Will there even be need for traffic lights? If the cars can talk to one another, they'll know who can go through the intersection. Imagine the opportunities for increased productivity and reduced traffic congestion and better operating and working of our cities themselves if we can get to this model. It will be quite advantageous for us to be able to leverage these new capabilities. So you're going to start seeing streetscapes that look something much more like this, that will allow pedestrians and cyclists and sidewalk to magically blur and blend in with regular street lines, because we won't have to worry about safety features that may have needed to be there before for people behind the wheel of a driving car, when the machine can make the appropriate discussion. Here's an example. If you think about all the items that are within our city for traffic management, whether that's curbs or lane markings or street lights, traffic lights, parking, red light cameras, things of this nature, we could truly reinvent the way our cities look when we start looking at these things. The same with parking lots or car parks across our cities, to be able to reclaim a lot of that space, because the cars can just move on to some other better use for their utilization, and we can start reclaiming some of the space that was, at least in early cities, designated as just large gathering locations and town squares, if you will, for a city. Same thing with our redevelopment of our neighborhoods. When you start thinking about how our curbs are set up with our parking, either on street or off street, what that can mean for change within our environment, probably much cleaner, healthier, and better, and be able to make our cities more connected again. Lots of good opportunities there, but it's not just in small streets. It could radically change the way we do our highway systems. To be able to think how, if we have lanes of traffic that might alternate during the times of day for commuters coming into the city in the morning and leaving in the afternoon, we have a typical rush hour pattern. Well, if the cars can communicate, we could do dynamic lane changing at any time and even have them go around one another if needed be, and utilize far less space, take out many of the street signs, street lights, all the traffic management things that you have, and start reclaiming some of that land for additional transport uses or even park space. So this is going to have a tremendous effect on the way business leaders approach their world. And one of the things you're going to need to figure this out is how neural networks basically let computers think much like your brain would think. Now, MBA students are very familiar with ways that we make decisions using regression analysis or decision trees. Neural networks take that to a whole nother level, where you might have hundreds of thousands of parameters that are much more complicated being brought into these models, and many more factors being brought in to be able to understand a business problem and solve it better. And neural networks is basically trying to think much like a human brain would. Now, we don't know exactly how the human brain works, but we do know it does send electrical signals from cell to cell, which are little spheres of knowledge from memory and also information that we have stored. And that information goes down our cells, and each little cell has a sphere of knowledge that it imparts upon the process as it kind of moves down the line, if you will. And so this is, neural networking is really just a way to think of a computer system that's modeled on the human brain and our nervous system. And we've seen many things already done with this. We recognize someone's handwriting. Computers can do the same thing. So say handwriting on check processing or speech to text. Your ears naturally hear the speech. It translates it, understands that, puts it into something you know. Weather prediction, facial recognitions, you know what someone's feeling by just looking at their face. This is now being brought into the computer, and the computers are doing the same thing. They're analyzing your audio signals. They're analyzing your handwriting. They're analyzing the look of your face for facial recognition to understand what it is you're communicating, either directly or indirectly. And so these neural networks basically mimic the way the human brain does this information. So when we bring information in, it usually is through our eyes, let's say. So we'll bring in the first layer, the input layer, if you will, might be raw input of information from our eyes. And that information goes to optic nerves within our human visual processing, and it goes through a different layer of network. And rather than getting information from our eye, it goes through successive tiers within our brain. The model keeps kind of firing along as it goes through, and it learns from each little signal, if you will, and it goes further down, deeper into these hidden, deeper neural networks of nodes within information. And so the last tier is what produces the output. So if I know this is water, and I see this is water, and I know if I open the bottle and I pour it on myself, it's going to get wet. How do I know that? How do I know water is wet? How does my memory remember these things? How do I know a clear liquid that's in this type of shaped bottle is water versus something else? These types of things that are in our nerve system is the same thing that a machine has to learn over time. And each one of these little nodes, if you will, on the network has a sphere of knowledge with it. And each of those nodes are connected to n number of nodes behind it, n minus one inputs for the next layer. So every node on each layer is connected to every other node of the next layer, which provides another level of information that allows us to process it as it goes through. So for this example, I have a memory of swimming as a child, and so therefore I know this is wet, and I'll know I will get wet. If I caught a cold because I swam in the winter, I know this could also catch a cold, but I also know it could freeze and form an ice cube. These are memory sets, even though none of those are happening here. So each one of these is interconnected, and the more we go down these deeper networks within this neural network, the deeper it gets. And this is why you see all these interactions and changes between the nodes themselves. And each one of those nodes is connected to the next layer of the node. It's not as if it's a critical path model, if you will. It's where the input comes in, is processed within the information it has, and each successive node. Now, the number of nodes you see here can be quite large. We're just giving this in a more simplistic form so you can see it visually on the screen. But each one of these can perform different layers. And so here we have 3 hidden layers in our deep neural network, from our input layer, which is the raw data, to the output layer, which is the answer we're looking for. You could have many, many deep levels within your network. And that's why it's a little complicated for us to understand as humans. Now, in this example, what if we wanted to just see what handwriting recognition was for numbers? So we take a square that someone's written a number in, 28 by 28 pixels. That equals 784, 28 by 28, 784 pixels. And we analyze each one of those pixels for whatever number that we're seeing. And it will go through successive layers and says, okay, is this pixel on or off for that one of those 784 pixels? Well, the corner might always be off, but somewhere in the middle one is on. And if I see a pattern where they're on with curves or shapes or bars or lines, based on what the computer knows from its model, that, say in this example it's a 1, it's one straight line, if I see that pattern, and those are the only patterns that I recognize, then I'm going to guess it's a 1. So here we have 784 input features, which is a pixel of a 28 by 28 store, but we have 10 outputs, 0 through 9. And the computer gives its very best guess at what it thinks it is, and it tries to figure that out on what the number can be. And so the great thing about this is these systems are adaptive. When they get them wrong, when the model isn't quite correct, it will analyze that information and it will basically weight itself. It has like inputted weighted values, if you will, on each of these different layers. So if there are, in our example of 784 layers, each one of those little lines could have a weight associated with it. And if it gets it right, it will weight it higher. And if it gets it wrong, it'll weight it lower by positive and negative values. And so it will go through this process time and time again until it figures out the right place where these weighting algorithms should be. And it'll look at various pixels within the place. And each one of those layers within the network, each has a weight. And there can be multiple weights and multiple inputs of spheres of each layer with multiple layers. And this is how we start weighting these numbers to see, does this give us the right value or not? So we're building a model. We're not saying this is what a 7 looks like or what a 4 or what a 2. This is a weighting of tell what these arrangement of pixels should look like. And then you can try to figure that out. So if we put this towards facial recognition for humans to sort of say, okay, I can try to see what your emotion is. You can see on the left, very easy to figure out what's, happy or sad, or someone that might be angry. But if you look at the ones on the right, the nuances are very much harder to figure out. Now, as a human, you can kind of look at someone. Maybe the eyebrow is turned a little lower, or the jaw is clenched, so you know that might mean anger. But even just a small smirk could mean happiness. Computers have a harder time figuring that out, so they have to go through multiple iterations of these to really perfect the model to understand what happiness looks like, or understand what anger looks like. Matter of fact, here's an example from the former Pakistani Prime Minister when he went on camera to address the constituents of his country after the Panama Papers scandal. And using the API, the Emotion API from Microsoft that allows you to feed in images, basically a video feed, using this artificial intelligence algorithm to basically rate levels of anger or disgust or happiness or content or surprise. And you can see at the beginning of this video, he was quite angry over what was being said, being very, more defiant, but started to get more upbeat and happier as the situation went along. And you can tap into this Emotion API that's out there by feeding in a video for this. So this is a great way to see that Microsoft has done the work of looking through thousands and thousands of videos, millions of videos, and perfected a model that they think is pretty close to say, is this person angry? Or is this person happy in this video? And how does it change over time? Now, as a business leader, you're going to have to build these models yourself within your company. Your team probably will as well. So you have to figure out what's the cost of doing this. It's going to take some time. What if you don't have this Microsoft Emotion API that's available there? So you probably will start with very cheap, large data sets. And what I mean by cheap sets, the ones that just help you build the model out. We call them pre-training data sets. But then when you start getting the model a little bit better and you're starting getting some results that you're expecting, because remember, the first one you feed in the answer with the item and the question that you're putting in, you can fine tune it. And so that's where you use very expensive, well-labeled data. It's basically a performance boost to the building of your model. And of course, you don't want to buy expensive, well-defined, highly intensive with human people involved data sets at the beginning, because it could be quite expensive to figure this out. So you might have a very cheap data set, a very low-cost data set of a bunch of numbers, or if you're trying to identify food, calorie counts, or any other type of model, you could just feed it in lots of pictures of food and say, okay, go figure what these out are, figure clusters of these. But then you might use a training set, a much more higher cost training set that's clearly defined what the numbers are, what the food is, so there's no guess, there's no ambiguity to it, so the model gets built up even faster. Now, the great thing about doing the numbers, they're only 1 through 9, but the MNIST database is available. It's a publicly available database. This was done by researchers at Google and Microsoft and others who put this publicly available out there with thousands, maybe millions of handwritten numbers. They've gone through line by line and looked at them with a human and said, yep, this is a 2, this is a 4, this is a 7, this is a 9. And so you can utilize that tool set to actually be able to train your data, because you know it's a well-defined, clean data set that's easily set up, and so you can feel much more confident in any handwritten number that you submit to it, that it'll have a pretty good chance, pretty accurately be able to identify what the number is and do so, like I say, accurately. And so as you start doing this, you'll want to be looking for particular items. So in medical data, you're looking for people with disease, or in credit scoring, you're looking for people with bad credit. This is the one that you're worried about. But in health data, most people are not sick, most are healthy. And in credit scoring data, most people do not default on their loans. Maybe only 1% to 2% do. So when you start feeding in the data that you're looking for, the unhealthy people or the people that have credit defaults, you have to be cautious there, because those data sets, clearly defined and well determined, could skew your model, because in those data sets, they're naturally skewed away from the norm, away from the population, because most people are not healthy. Most people are healthy, and most people do not have bad credit. So just be aware of that as you and your teams build out these models to create these. Now, it's going to be hard, but there are lots of companies out there that can help you with it. Amazon, Google, and Microsoft for sure, all these 3 of the biggest, that will provide a lot of these to you on a more complementary basis because they want you to build these models in their enterprises and on their clouds. But there are many companies out there that can find and help you with training data sets, sell you data sets, rent you data sets that will help bring these models together faster so you can optimize the work that you're trying to do. So let's take an example where you might want to do a situation where you have facial images with age progression. Maybe you need that for some reason. So let's say you need to train a data set that says, how will people look when they're older? So what we're going to need is lots of people that are 10 years apart, any 10 years, doesn't matter, because maybe we're doing age-specific ad targeting. That's the source that's paying for this that we're going to spend a lot of money to go do and a lot of time, effort, and energy. Well, if you're familiar with the recent Facebook 10-year challenge, you actually had a lot of people voluntarily give you side-by-side fairly good images of then and now of 10 years apart. And what was really interesting there is that so many people did it, from movie stars to just everyday people. And you got a really good public data set that you could actually utilize across a variety of ages that were all, for the most part, 10 years apart. So you might be able to find these data sets relatively inexpensively. You just might have to use some smarts about how you might go about doing it. This would be a prime example for a place that you could do that. Matter of fact, the Indian police have used this, much like the movie Lion, to help find children in that very large country that have been missing by using facial recognition through cameras that have already identified 3,000 missing children just within the 4 days of use by looking at what a child was, how old they were when they got lost, and then using this type of analysis to say, what would they look like 10 years from now, 8 years from now, because I have a model that kind of fits that, so they probably look like this. Feed it in, look for cameras for it, and then be able to find the right person. So lots of good things can come out of this technology. But you need a large data set to do that. One place to go might be ImageNet. ImageNet is basically a large image data set with a WordNet hierarchy based upon it that is human annotated. It's a .org site, so they offer many out there, and it's expanding every day. Tens of millions of clearly sorted pictures and images of items. So they use this word tree type of model for object detection. So if you know what's in the picture and you know the word associated with it, you can then feed it into your model. So in this word model, we know there's a physical object, which could be an animal. That animal turns out to be a cat, and that cat turns out to be a Persian cat. And you can see how you work down your way through this word tree for object detection, going from just a physical object that might be in a bounding box to actually knowing what it is by utilizing this model that's been fed out from this ImageNet service. So let's talk a little bit about artificial intelligence and how it's going to really help you as a business leader make some really good decisions. So just think about it for artificial intelligence. Really, this is the ability for us to learn about and learn from and understand and interact with our environment. That's what we consider intelligence. So artificial intelligence is just the simulation of that in a machine. That's all it is. It's just the same way we would use intelligence. So these are machines that are programmed to think, if you will, like a human. They basically mimic the same type of synopsis process that we have in our brains to go down these machine learning models to figure things out. Because if we know what they are, we know what's in the image, we know what's in the video feed, we know what's in the trajectory of the camera that the computer's looking at, if we can clearly identify that, then we can say, okay, what's the next reasonable step to actually rationalize the information that comes in and take some appropriate action, just as we would do as humans. If we saw a car racing to us, we would step out of the way. The machine can do the same thing. Because it knows, that this is how it could be programmed to rationalize, say, oh, there's something coming this way, let's step out of the way. So this is the same way. Well, I'd like you to watch this little video that discusses a little bit about how this world is evolving. It is from Google. Google's a very strong leader in this space. It'll give you a little bit better understanding of what this is meaning for us and the changes it can bring.
You ready to start right now?
Yeah, thank you.
There have been a number of shifts in the way we think about computing over the past few decades.
The terminology artificial intelligence has come in and out of favor in the scientific community. Sometimes it's called machine learning.
We tend to call it machine intelligence these days.
I just call it intelligence.
And sometimes it's just the effort to build machines that are better.
So in the early days, everything was built on logic, doing mathematical integration problems, playing chess. But we realized that what the real challenges were the things that people can do every day.
The real world is actually very messy. Hard logical rules are not the way to solve really interesting real-world problems.
You have to have a system that'll learn to get the knowledge in. You can't just program it all in.
Artificial intelligence is an effort to build machines that can learn from their environment, from mistakes, and from people.
And we're still at the stage where we don't know what is the right path and the right breakthrough.
So, I mean, there's certainly a whole raft of different approaches.
One of the subfields we call pattern recognition.
Artificial neural network,
Reinforcement learning, for example.
statistical inference, and probabilistic machine learning.
Supervised learning, unsupervised learning. And we're not quite sure what technique is going to lead to better systems. And in fact, it's probably not one technique for everything. It's probably a bunch of different techniques and combinations of those techniques.
Any progress we make in building truly intelligent systems is going to depend on progress in technology generally. And until recently, we didn't have computers that were fast enough or data sets that were big enough to do that.
And so being able to take a particular problem and spread it out over lots and lots of machines is a very important approach because it makes our research faster.
So there's applications of artificial intelligence around us all the time.
When it begins to work, or it does work, it's all of a sudden given another name.
We're all already using it and very comfortable with it.
Things that now we regard as routine, 30 years ago would have been regarded as amazing examples of artificial intelligence.
Anti-lock braking,
Autopilot systems for planes,
Search.
recommendations.
maps.
To decide whether or not this particular email is spam or not spam.
The ability to translate one language to another with your phone. 10 years ago, if you tried to talk to your computer or to your phone, you know, that would just be hopeless.
We are seeing a steady torrent of these tricks, one after the other, getting figured out right now. And I think a lot of people that are close to the field have this, do have that kind of breathless sense that things are moving quickly.
It's a progressive thing. It's about building things that are slightly better, slightly better, slightly better.
Intelligence is really not going to be something that we ever succeed in defining in a succinct and singular way. It's really this whole constellation of different capabilities that all kind of are beautifully orchestrated and working together.
Predicting the long-term future is very difficult. Nobody can really do it. And the bad thing to do is take whatever's working best now and assume the future is going to be like that forever.
So one of the things that's interesting with business leaders is the things that we love to do the most, such as developing our people or engaging with our stakeholders or solving problems or doing strategy and innovation, is probably the least thing we do. We do 54% of our time, at least according to this Accenture survey, on administration and coordinating and control. This is the pieces of the job that could probably be done by a machine thinking rationally on administrative functions and allow us to focus more on the things that really can add good value, which is strategy, innovation, problem solving, and working with our team. Now, there are various industries that are taking advantage of this more than others. Information technology obviously is doing one. They're doing fantastic jobs with deterring security intrusions, looking for patterns that they've seen in the past. So a human doesn't have to do that. Matter of fact, a machine can do it far better and monitor a network or look for intrusion issues. Marketing is doing very good with this, with improving media buying or trying to tailor promotions online or offline to a specific demographic or target group, or sometimes even the direct person themselves. Then, of course, accounting and finance with high-frequency trading, and then customer service for automation. When we start talking to bots to actually respond to our needs and answer us sometimes better than a human could. Yet it will perfect over time and just get better and better. And so there's areas where we start seeing this more and more that business leaders need to take a look at. One is obviously natural language processing for things like customer interactions. Also, product recommendations when you start thinking about cross-selling and upselling opportunities to understand your customers better and who they are and what they might need. Medical diagnosis is a big area because a computer such as IBM Watson can scan through so many more x-rays of radiology x-rays and help make a determination to actually confirm what the doctor thinks and say this is a good confirmation because I've looked at millions, you've looked at maybe hundreds in your lifetime. Let's work together and give suggestions for what they think the diagnosis could be, or also a confirmation of what the doctor thinks it might be. Little tasks like manual data entry, detecting junk email, financial analysis, image recognition, obviously we've seen through computer vision, or customer segmentation or lifetime value prediction, all being much more utilized with artificial intelligence. Matter of fact, the banking sector is doing a pretty good job of this in certain areas, especially on fraudulent items, payments, security issues. Less so if you see on the lower right here with, the lower left, with improving interactions and direct communications, if you will, with customers, more front-end banking application work, but still making good progress. So financial services is a big area for this. The other thing you want to look at as a business leader is to understand where the innovation and activity is happening. This is the number of companies that are working in this space, and you can see machine learning is doing well, personal virtual assistant, speech recognition, all the way down to video content recognition to understand what it is that you're seeing within the video itself. And then also another place that a lot of business leaders look for what's happening here is what's happening in the exit activity with these startups, these companies that are coming on with these great new AI abilities. And notice here, most of them are being acquired. There's a few that have gone public, especially in the machine learning space and maybe smart robots, but most is being acquired. And where they're being acquired is by the big corporations within tech. And Google is on a tear here. As you can see at the top of the chart, they've been doing extreme number of acquisitions in this space. Apple's biggest one, Siri, obviously that's a very artificial intelligence way to communicate and talk directly to a computer. Their first big one was with Siri, and it was a large one, but they have gotten back into the game, Facebook and Amazon especially. So the pace is not only high, but it's accelerating as we go along. And it's really interesting to see how this is also affecting strategy between countries as well. You can see here how the world is making gains in this area. China and North America by far leading it, Latin America lagging the most. But if you look at where venture capital is being invested in this space, the U.S. still leads. 51% of the world's total VC money is going in this space is going into U.S. corporations, 14.8 billion, but still 33% of the world's total going into China. And these two countries, without question, are leading in this space to try to see what's going to happen here. Part of the reason China is doing so well is they have actually put this directly in their China 2030 plan, and they have said as a country, China is going to be an AI leader. What's interesting here, they have surpassed the United States in the number of white papers on this particular topic, but the U.S. papers tend to be cited more, so they might be of a different level of quality, just to understand what you're looking at here. But when you start talking about where the financing deals have happened, China has already surpassed the U.S. U.S. is typically very proactive in doing financing for venture capital and things, but China has now surpassed the U.S. And is doing quite a bit. But as far as the people, the part is the really, really smart people that are doing this, the U.S. still holds the lead here. There's really about 1,000 people that are capable of steering this industry. And this is coming from Tencent in China. And there's maybe a need for millions of these people, but there's about 300,000 people on the globe today that work in this space. Most are at these companies, and you can see Google is by far leading it. So with IBM and Microsoft and Google and others taking that lead, Facebook still on the top, the majority of the mind share of what's driving this industry still coming from the U.S., but don't discount any from China because Tencent and Baidu and others are coming up very much so. So one of the other things I hear a lot on how this is going to adjust the economy and how we as business leaders are going to have to deal with this is in unemployment and where employment changes are going to happen. So you can see here that there is a net job creation and net job loss. by industry through the year 2037. This is according to PwC. Health, scientific needs, communication, hospitality, education will still stay high. But things like manufacturing and transportation, finance and insurance will have a net loss. So as a business leader, you're going to have to adjust your corporations to be able to deal with this new scenario. Matter of fact, it's not really a matter of how this is going to change. The change will occur, but currently less than 5% of the occupations that are out there can be entirely automated. But about 60% of the occupations have at least about 30% of the tasks that could be automated. So what's going to happen is things are going to move to the place where they have the greatest comparative advantage. And so where machines and robots and artificial intelligence enabled devices are going to be more prevalent and do better than a human, they will win there. But in the creative space, or things that take more empathy, or things that require more understanding of a broader base, humans will do better. So there still will be jobs for humans. But each are going to go to their comparative advantage, and hopefully the less impactful jobs, the more menial jobs will be done by machines, and will allow humans to be able to do more enabled, more creative jobs, ones that actually bring more value to what we want to do. So the question won't be not if we lose our jobs, but maybe how much we'll get paid to do it. Because if a machine can do it cheaper, and right now they're quite expensive, a human will still be able to do it, and a human won't lose the job to the machine. But if costs come down and machines do it better, again, comparative advantage, the machines will take it over. Then it determines, can we compete against the machine? When you start thinking about large countries, and notice everyone here on this chart is in the 40s, 50% range of all the potential opportunities for automation to affect employees, it's quite large. So if you're taking half of the global population, the working population, the employees, it could be a significant change to global economics. And of course, you see the two extremely large ones here, China and India, just with the sheer number of people that this change will affect. McKinsey & Company did this study to really help you understand this. Another view to help you see how the number of employees by country, of course, China, India, they're at the top, United States not far behind, for where potential for automation is going to affect those jobs, the ones in green being that 50% mark. And it even breaks it down by sector. So we see agriculture, manufacturing, and retail trade being quite significant. But also at the bottom, when you start looking at things like management and utilities, those will also be affected, because about 50% of those jobs, even though there are less of them, will be affected. So this is going to go into public policy debates on how we retrain and retool our societies and our citizens to be able to have very well and productive jobs. So this is going to have a lot of business impacts for your strategy as a business leader. And we've talked about how these technologies build upon themselves, from cloud to big data on to machine learning, and now once we have this knowledge within the machine itself to use artificial intelligence to understand things. And you must go through this type of segment if you're in the technology industry. Now, where you get in on this phase depends on you and your company. So for Amazon, they started very early with cloud computing and utilized that to leverage big data, and utilize that to understand better through machine learning, and then use artificial intelligence to actually start making things more efficient, say in their distribution warehouses or their shopping algorithms for suggesting products. Now, Uber didn't do the cloud. They actually jumped in and utilized someone else's cloud, Amazon or Google or Microsoft, but they did use big data to come up with a better model or model to create their product, to service their customers. And now they're using machine learning, of course, artificial intelligence, as they start getting into autonomous vehicles to do local transport, which is their key. Where your company come in could be later down the line. Maybe you're actually going to be able to enable it enough to actually just use artificial intelligence tools that are hosted by someone else, like a Microsoft Emotion API, and leverage that to a new business model. So you don't necessarily have to go through that path if you can find the right place that you can pull yourself into. So there's a lot of things where a business leader should look for to try to go next. So you often ask this, okay, now that we understand AI, we understand what it can mean, where do I take my business? And what I would say is you should look for areas where customer needs are not met because of some extreme complexity or some extreme customization or some extreme cost. So something like complexity would be gene editing, where artificial intelligence is helping us understand this model and do it better. Or extreme customization might be prosthetics, where every single prosthetic needs to be created for that individual customer, that patient, if you will. Or extreme cost, such as supersonic travel, and the startup boom is attempting to do that. There is, without question, demand in the marketplace for supersonic travel, but it was such extreme cost that it couldn't be done effectively before. And this young startup is utilizing new design techniques within aerospace and the design of the plane itself without ever having to build one. It's all being done in the computer to be able to come and address these things. So look for known market demands where there's no current solution offering. And I would challenge you to go look at past projects that were deemed unfeasible in the past. They might be feasible now that we have these technologies, or even dream solutions. You know, space travel is a good example. There is, without question, a demand, a marketplace for space travel. Can we make it low cost enough and safe enough and cheap enough by utilizing some of these technologies? Or flying cars, or the dream solutions like weight loss. Eat anything you want but never gain weight. There are things that can be done now with artificial intelligence to better understand how the human body works, how we can manipulate, how we can help create healthier outcomes for patients that could lead to amazing solutions. So when you start bringing these new AI opportunities into your firm, you really want to think about the specific issues, maybe not the entire system. Because if you address it in just one item at a time, it can be much more faster and much more practical. So let's say your goal is autonomous driving. So Volvo looked at this, and they also looked at some of the issues around autonomous driving. They need not to crash. Cars should not crash. That's a good thing for them to sell to their customers. So the biggest cause of accidents was rear-end collisions. And so if they had automatic braking, if the car was smart enough to know something's in front, stop it, it could solve that issue. But you wouldn't need emergency braking if you had a fully autonomous vehicle. The vehicle would already know. This is when you have a human involved. But this is a great place to use one specific item. So rather than designing an entire car that could drive itself, just focus on the front of the car using LiDAR and artificial intelligence to understand what is in front of the car, pedestrians, cyclist, another car, and if the car is getting too close, apply the brakes. And the company's going to get smarter and smarter at that, and then maybe take that knowledge and be able to put it around the entire car, which is what's needed for an autonomous car. Now, why are they doing this? Because they know they're going to have to. If you look out by 2035, clearly a quarter of the cars are going to be fully autonomous, and that's going to switch over around 2025. So it's not very far away. So they've got to start somewhere, and you've got to find these areas within your enterprise where you can bring in an artificial intelligence to solve one part of the bigger picture, learn from that, and then build over time. As this is what it's going to take as we build through this. So the other thing you want to look at is when you bring AI in, figure out a place where you can prototype it and then commercialize it. Basically, you want to test it, you want to iterate it, you want to fail it and fail it fast if it fails, and then repeat it. Part of what we've learned in this video is that models through artificial intelligence are built through repetition, and they built over time. Same thing with the way you would want to do this prototyping for AI. So basically just limit the scope to ensure the success and then build from that success. So if you look at what Waymo did with their driving technology, this is the Waymo van today, but it did not start out that way. It started out with the Firefly, and the Firefly was basically kind of a car, but didn't have a lot of the car features that you would normally think. It really wasn't intended to be a mass market product, but they did have to learn from it to figure it out. It basically only went 25 miles an hour. It was missing a lot of the typical car features that you might think of. But they learned from that. And one of the things they learned was they learned that a central rooftop LiDAR sped up the data processing that's needed for really quick reactions. So they put one central unit in the middle rather than all around the car, which some other companies do. The other thing they noticed is when passengers were riding in this autonomous car, they felt unease because they didn't know what the car was seeing. So passengers want to see what the car saw. So it's this level of confidence. So they actually put a screen in the car that shows kind of a computer vision of what it sees as the world around it. So it knows that it recognizes the car beside it, or the pedestrian on the sidewalk, or the cyclist up ahead. And it just made the human feel much easier. So you got to think through these kind of models as you bring these kind of new technologies in. The other thing you want to do is use AI where you can afford a mistake, if you will. You know, AI learns from these continuous feedback loops, and it learns it from wrong decisions. So deploy where the mistakes won't significantly hurt either your reputation or the customer experience. And a good example might be in smart homes, when the thermostat recognizes that you've left the house, it'll turn off the lights and turn down the thermostat, maybe turn on the alarm. If the thermostat doesn't go off, if the lights remain on, it's not going to kill the process. It won't be ideal, but it's a way to learn through. So as the mobile phone, which has this automatic away mode, physically leaves the home when you do, the system will automatically know, oh, this person is away, therefore I can turn the heat down, I can turn the lights off. But if it doesn't happen, it'll be okay. And so let me give you some business examples of where industries are doing this. And I truly believe this can be applied to any industry. And that includes the mining industry, probably one that you just don't think of as being leading edge. But definitely Rio Tinto does. They're the large mining conglomerate. They have just invested $2.6 billion in an iron mine in Western Australia. It opens in 2021. And basically everything in this mine is going to use artificial intelligence. They're going to have autonomous drilling and digging. They're going to have autonomous trucks that will go out and pick up the materials. They're going to have autonomous trains that will take it from the site to the port to be able to be loaded on time. And they're even using this with GPS. They call it their kind of pit to port ratio, where they can make have the machines make the decisions themselves. So using GPS, they know the boat is so far offshore, they can estimate when the boat will be in port, and they can have the iron ore sitting there at exactly the right time to arrive when the boat arrives, so you don't have excess material waiting on the ship dock, waiting to be loaded onto the ship to move on. They're even incorporating things such as real-time analysis of global demand, so they should be digging faster in order to get it to the truck on time, to the train on time, to the port on time, to get it to the demand it sees and it's projecting in the forecast for global demand for iron ore. They've even created a digital twin. Now, you'll hear this term a lot as you go forward, of creating a virtual reality version of whatever it is you're doing. So they've created a virtual reality world of this mine. They can be in a major city and walk through the mine using virtual reality to help solve issues, solve problems, have a geologist look at particular things within the mine itself. Quite interesting. And so these things are happening to improve operations in one of the most one of the oldest industries out there. Let me just put it that way for you. So another good example might be what Pinterest is doing to leverage the huge collection of data that they have in photographs to be able to identify products in the photograph itself and have single click to buy and be able to get something that you saw on Pinterest and buy it directly. The other good place that many of you might have in your home are these smart speakers. Obviously using artificial intelligence to understand what we're saying and respond to us in a great way. And they've actually gotten better than us at this. Humans have a 5 to 6% word error rate. These smart speakers are now down to 4% and going lower. And you can see with Amazon Echo, with more than 50% of the market share, they are learning quite a bit more, because obviously more data leads to better models. Other examples you see it every day is in YouTube with direct conversion of video captions on videos to different languages that's not in the native language that the video was shot in. Another example of Everlaw, a law firm that's using artificial intelligence to do e-discovery, to go through thousands and thousands of documents and then tell the lawyer in advance which which file they should look at ahead of time to be able to investigate for a particular case and to prepare for trial. Obviously a great place where humans and computers are working together. This is a unique example for Wibbits, and Wibbits has taken text articles, typical news text articles that a news organization might make, pull out the keywords as it searches through the document itself, and then from those keywords and what it thinks the article is about, we'll compile little video segments based on those keywords and put together a video file, a video version of the article that can instantly be published to a medium such as YouTube or any type of the web-based mediums. So instead of reading the article, you can watch the article. and be able to pull that together. Here's another example that was done by Caltech as well as Disney and the Stats Company to basically look at all the data that they had on competitors for a soccer league and actually understand how teams and how competitive teams would react in various situations. And once they built a model of that team, they basically did a machine learning model of the team, they can feed it different scenarios that the opposing team could do, different plays, and see how that team would react and see what the percentages of success are. And therefore utilize machine learning to say, hey, for this particular team in this particular situation, you should use this particular type of play and you'll have a better chance of beating the team. So another good example there. There's lots of impacts that you're going to see. One is obviously in the automation of transportation, and this includes long-haul trucks and trains and buses, also vehicles for delivery, both as personal. We'll see this in health improvements, specifically on diagnostics, but also treatment of incurable diseases and even remote surgery assistance. Fraud detection in the banking industry, also the automation of very dangerous jobs like bomb diffusion, and you're already seeing that happen in bomb diffusion, but welding and mining and things where humans really won't want to do this type of role. The other example for tremendous opportunity is the environmental issues. These are extremely complex systems. When we start looking at global warming and what is happening to our environment, artificial intelligence can process so much more of this data to create a model that more accurately predicts what's going to happen and maybe ways we can help prevent some global warming issues. Expedited judicial proceedings by basically going through evidence in advance, customer service, visual recognition, classification, and tagging, algorithmic financial trading. This is that high-speed financial trading that we see a lot on financial markets. And also intelligent recruitment and HR systems to be able to see how can we find the best appropriate person that could fill a particular role for us. And also converting paperwork to digital data, which has always been a big process for us here. But we're going to see this with helping solve lots of global problems in healthcare, safe transportation. Matter of fact, if we look at transportation, and the World Economic Forum did this, if you look at automobile accidents, which is the lowest line in this chart, it's actually going down in rich countries, but in emerging markets where more people are getting cars, that rate is going up, and deaths are actually getting to the point predicted where they will surpass HIV and AIDS. So automation and the ability to have intelligent vehicles will help save thousands of lives in this respect. When it comes to energy usage, Google did a great model where they actually utilized artificial intelligence to actually monitor and control heating and cooling elements within their data centers. And they turned it on for a while, had a 40% reduction in electricity usage, turned it back off and went right back up again. So here's a good example where machines are obviously doing much better than humans, and this is going to save a lot of money. But even something as good as wildlife assistance, to be able to use prediction models to understand animals' migration patterns. So if we as humans keep encroaching on their environments, need to build something like a natural bridge to allow them to get across a barrier as a road or a train track, to be able to understand that better, AI can help us figure that out. So we're going to see this continual evolution, and I actually see cloud computing kind of decreasing in the importance of it because, as you remember, we had the ability for clouds to allow us to access data. Big data was what allowed us to develop these big data sets. And once we could do big data sets, we could analyze it easier. That's what the machine learning came in. And of course, once we've analyzed this data set, we can enable it to be understood. And that's where artificial intelligence come in. But the great thing about this is just part of a pattern of how technology switch changes over time. So we started with the mainframe world, which was very centralized in its work, and then we went to this more client-server model, to today's model where we have a mobile-enabled device that's powered by cloud computing. And mainframes and this cloud-powered mobile cloud connection are all centralized, and they're centralized through some major corporations today, Google, Amazon, and the Microsoft Azure platform. So when you have this type of centralization of power, you may not have the most appropriate innovation that comes from that. So the client-server world was a distributed computing model, and we saw tremendous innovation in the 80s and 90s when that model came in, because we distributed the capabilities and we had lots of new things coming about from innovation. I believe our next model is going to go more to this edge intelligence, and we're going to see that in things like cars. So the actual processing of the data itself in an autonomous vehicle is going to occur in the car. The processing of the data is going to occur in the car. What's going to come from the cloud are learning updates, models that help the car operate more effectively and understand its environment better. And it'll still take in the data, say from cameras or LiDAR, make an effective decision based on the model that it was downloaded, and then quickly, very quickly, apply the brakes or make a turn or whatever it needs to do within the car itself. And remember, when we had the client-server model, there were lots of competitors with lots of innovation. I think when we get to this edge intelligence space, we're going to see the same thing. There's going to be lots of competitors and lots of innovation once that more distributed computing model comes back into vogue, and we have lots of young startups being able to create these things. So remember, I mentioned to you that the whole data is the new oil. Oil was basically the piece that enabled the revolution. Data is what's going to enable the digital revolution. So as business leaders, what I want you to do is think about artificial intelligence as really the new tool for you to figure out what you're going to use these new tools for, and these paradigms it's going to create is going to be up to you. And when we do that, that's where we're going to really create some significant impact in the industry. Thank you.